Okay. So last time we showed that, okay, a new proof that 1 is the only harmonic integer. Okay. So remember, a harmonic number is this. Okay. Okay, so assume to the contrary that some n larger than 1 is a harmonic integer. Okay, so you add up these things and you obtain an integer. Okay, so to reach a contradiction, we choose a prime. So let P be the largest prime less than or equal to n. Okay, then let's see what we do. Then we claim first that n is strictly less than 2p. Okay. If not, okay, so if not, we'll contradict that p is the largest one. So, okay, so this is the part. Every time you use a heavy theorem in a proof, the proof becomes easier. So here we assume this famous theorem, Bertrand-Chebyshev polynomial, Chebyshev, how do you write this? Chebyshev. Sometimes you put C there, sometimes you put theorem. So if not by Bertrand-Chebyshev theorem, there is a prime. There is a prime Q such that P less than Q less than 2P. Okay, so this is a very famous theorem. The proof is quite long. There is always a prime between n and 2n. And in fact, it even has a stronger version between n and 2n minus 2 something. So you can shave off a few things. Okay. But of course, as n becomes larger, the interval where you will find the prime becomes larger, but it is guaranteed that there is always a prime strictly between a given integer and its double. Okay, so we use this now. Okay, so when we said if not, it means that we are saying that 2p is less than or equal to n. Okay, so if 2p is not strictly larger than n, then it is less than or equal to n. But okay, here you already obtained a contradiction because p is the largest prime less than or equal to n, but now the theorem says that there is another prime q here. Okay, so this existence of this prime less than or equal to n contradicts how we chose P. Okay, so now we know that this holds. Now the rest is we'll multiply both sides by n factorial. Okay, so now we have P largest integer, prime less than or equal to n, and this is less than 2p. Okay. Multiply by n prime both sides of hn equals 1 plus 1 over 2 plus somewhere here we have 1 over p plus 1 over n. Okay, so this p can be the last integer, but it's there. So when you multiply this n factorial hn, okay, we have this here. Now here you have n factorial plus n factorial over 2. Okay, so let me write something different than p, and then somewhere here we have n factorial p. Okay, so n factorial n. Okay, now what we observe here is that p divides everything here except this one. Okay. So this is not divisible by p, okay, because n factorial is product of integers from 1 to n. P is the largest integer there. Once you cancel p, then there is no p left here. The next chance would be 2p. 2p could be there. Then this would be divisible by p, but 2p is larger than this. So once you cancel out p here, this number is not divisible by p. So this integer is not divisible by p. Okay, all other integers, all other terms are divisible by p. Okay, so you cancel something. Okay, so this now suddenly I started to suspect that there is a flaw in the proof. What do you say? So what about this next one here? Is it divisible by p? Because p will be cancelled. Okay, so if we have a term here, n factorial divided by p plus 1 factorial. P's will cancel, right? Then it will not be divisible by p. Okay. So anyway, so it's a nice. So this generally happens.
No, it's not p plus 1 factorial. It's p plus 1.
Ah, p plus 1, right? Good. Yes. So this is wrong then. Okay, so. Okay, so then it is still we are still good. Okay. So we are dividing by integers one by one. So once you pass p, no problem. Okay, so you are canceling other things. Okay, all other terms are divisible by p. Only this one is not divisible by p. So we have a contradiction. Okay, so left-hand side is divisible by p. Right-hand side, when you divide everything by p, so consider this mod p, all of them will give you 0. Only this one will give you something different than 0, mod p. Okay, so left-hand side, so p divides left-hand side, but p does not divide right-hand side. Contradiction. So what is the reason of this contradiction? We said assume to the contrary. So one is the only harmonic integer. Okay, so I like this proof because when you introduce some nice theorem here, you suddenly make things easier. Okay, so this is the strong theorem that makes the proof visible. Okay, so thank you. So now let's go back to our binomial series. Last time we wrote the binomial series. We showed how it is. We wrote the Taylor series associated to binomial series. So the question is this Taylor series equal to this binomial parentheses? Okay, so let me go over that very quickly, and then we'll start the process of showing that the Taylor series is equal to this binomial object. Okay, so let me use this. So back to our binomial series. So we observed that last time we observed that we can define the coefficients like this. we can define this for, I use C, so ck, C times C minus 1, C minus 2, let me emphasize this. So you go to up to C minus K plus 1. So you have K terms here. To make this more visible, I sometimes write it like this. K, there are K terms here. So we define this where C is any real number different than 0. Okay, so let's say C different than 0, and K is an integer. Okay, so I need K to be an integer because I'm multiplying these, but C can be anything. And of course, I have to define this when C is 0, you want this thing to be, okay, so and then we have C0. Okay, so I think I can take C0 here. It makes this 0. The problem is when you have K0, when nothing happens here, we define this to be 0. Okay, so that's how it works. So we define such things. So you see that when you put an integer in C, this is the usual binomial coefficient. Okay, so Newton claimed, and in fact proved, that if you have 1 plus x to the power c, this is going to be equal to the usual thing, summation n equals from 0 to infinity. Okay, so to be consistent with this, I'm using k here. ck, x to the k, and this holds for x less than 1. Observe that if c is a positive integer, this infinite sum is a finite sum. Okay, so for example, suppose this is c equals to, this is just 1 plus x squared. C is 2. So when you subtract c minus 2 from this, you get 0 here. So c2, c3 will be 0. Okay. And then the next one, you come here, but this was already 0. So this 0 will stay here. All the other terms will be 0. Okay? So even if we write this from k equals 0 to infinity, we will have when k equals 3, this will be 0. All the other terms will be 0. So this reduces to the usual. Okay, so note when c is an integer, this is a finite sum equal to the usual, usual binomial theorem. Okay, it is just by doing the cancellation in combination formula to observe that it can be defined for any c. Then Newton claimed that we can continue the series infinitely many times, and the result will be exactly this. So let us prove this. So we showed that we proved that, I don't know, I don't remember what we proved. What did we prove? I think we showed how to derive the series, right? Because the series is easy by taking successive derivatives. So let me quickly do this, and then I'll do in detail what we left. Okay. So we start by finding the binomial, the Taylor series of f of x equals 1 plus x c. Okay, so this is, we have f of x equals 1 plus x c. So f of 0 is 1. F prime x is c 1 plus x c minus 1. So f prime 0 is c. So we continue this way, and we convinced ourselves that if you continue this, you will have the numerator here, c minus 1, c minus k minus 1. So you see, I take the first derivative. This is c minus 1. Okay, so you do a few more terms, and then this becomes obvious. And then here you have 1 plus x, c minus k. Okay, so if you take the k plus 1 term, then you have c minus k here. So that is why we have this here. Okay, so we showed that this is true. So, so the Taylor series is summation n equals from, I'm using k because I started this with k. K equals 0 to infinity. The kth derivative at 0 divided by k factorial, x to the k. Okay, but now I know what this is. The kth derivative at 0 is this. I am dividing it by k factorial, so I have that symbol there. This is summation k equals 0 to infinity ck xk. Okay, so this is the Taylor series. Does it converge or not? So in order to check this, call this an. Okay. So for radius of convergence, we look at the limit. This is ak. Limit k goes to infinity, a k plus 1 over a k. Okay, so you simplify this. So you see it's easy because you are adding one more term here and one more term here, so those extra terms remain. This part is already the previous one, so they cancel, and all you have is limit k goes to infinity of c minus k from the top and k plus 1 from the bottom. Okay, so here leading term in k is 1, leading term in k is 1 in absolute value, so the limit is 1. And of course you have x here, because these things have x here. So the limit is x. Okay, so for convergence, this is less than 1. Okay, so far we showed that it has a converging Taylor series which converges when x is strictly less than 1. Sometimes it converges on the boundary. We will not go into this. Okay, so the question is now, this is where we stop. The question is, does this series converge to this function? Okay, so there is a tricky way of doing that. There are straightforward methods, because you have a remainder formula from Taylor's theorem. If you carefully, very, very carefully analyze the remainder theorem, you show that it converges to the function. But the book suggests a tricky but easier way, so we'll go for that. So now this is a function, okay? This is a function when x is between -1 and +1. We'll try to show that this function is equal to f of x, okay, on that interval. So let g be that function. So let g of x be this summation, k equals 0 to infinity ck xk when x is less than 1. We want to show f of x equals g of x. Okay, so we'll do this by finding some properties of g, and using that property, we will show that f over g or g over f is constant. And then we'll find what that constant is. That constant will turn out to be 1. So if f over g is always 1, they are the same. Okay, so that's the method. So the first thing is to show some property of this. Okay, so we claim that so what is this? 1 plus x times g prime x is equal to c times g of x. Okay, it looks like a complicated thing, but we have an exact formula here. We have the theorem saying that the derivative of this is summation of the derivatives of these. The derivatives of these are easy to write. So we'll just write this part and see if we get c times g of x. Okay, so for this thing, all you have to do is play with the general term here. G prime x is equal to summation. First, I start from 1, because the first term will be 0 anyway. K starts from 1 to infinity. K times ck x k minus 1. Now, I'll multiply this by 1 and compare it with this. So, and this one starts with k equals 0. So I make this start from k equals 0 by just playing with the coefficients. So this is c plus summation k equals 1 to infinity. Or, okay, first let me write the other one. So summation k equals 0 to infinity. So I make this k plus 1. Okay, so when k is 1, the coefficient here is 1. So I again want, of course, 1 here. When k equals 0, this is 1. ck plus 1 x to the k. Okay. Okay, so now we can use this. So to make life easier, I now observe that this is like this. Infinity k plus 1 c k plus 1 x to the k. Okay, now we write this part. We have g prime x plus c times x times, I have x there, x times g prime x. Okay, so this is c plus summation k equals 1 to infinity. Okay, I use this one, okay, for here, and I use this one after I multiply it by x, okay? So when I multiply it by x, I'll have x to the k, and for this one, I have x to the k, so that's what I'm trying to do now. Okay, so this is k plus 1 c k plus 1 plus k c k to the power xk. Okay, so this part, it's now this part. We write what this part is. Okay, so this part is easy. This is something divided by k plus 1 factorial, right? And I'm multiplying it by k plus 1. So this is something divided by k factorial. So what is that something? I start with c minus 1. And the previous one is c minus k plus 1. And the last one is c minus k minus 1 plus 1. So c minus k. Plus I have k here. Okay, so I have k here. I have k factorial here. This time I'm not canceling, so that the denominators will be the same. So now I have c minus 1, c minus k plus 1. Okay, so now you see that, let's take some color here. So this part is the same as this part. Okay. So let's write this. So what is this part? This part, the green part is ck, right? This is precisely ck. And what we have here is c minus k plus k. So this is c times ck. Okay, so we take this now here. This is c plus summation k equals 1 to infinity c times ck x to the k. Okay, so you see this is just now taking out c. This is c times g of x. Okay, so everything, we didn't do anything. We just calculated the left-hand side, and it turned out to be the right-hand side. Okay, so this was straightforward. Now comes the tricky part. The tricky part is easier, but to think about all ingenious things are like that. To think about it is the difficult part. Once you think about it, the actual implementation is easy. Okay, so next, define h of x as, let's see, which g of x, g of x over 1 plus x to the power c. So we want to show that h of x is identically equal to 1. Okay, so then that means these two functions will be the same. And of course, it goes without saying that we are working on the interval from -1 to +1. Okay, because otherwise, if this is -1, it doesn't make sense, and outside the interval, this doesn't converge. So everything is claimed where they make sense. Okay, so this is for x less than 1. Okay, so how do you show that a function is constant? You take its derivative and check that it is equal to 0. Okay, so this is where we will use this one. Okay, so h prime x is equal to g prime x 1 plus x c minus g of x times c 1 plus x c minus 1 divided by 1 plus x to c. Okay. So again, we take out something. You see 1 plus x to the power c minus 1 is common here. So I take it out, c minus 1. I also have this is cancellation, c minus 1. Okay, so what we have here is, well, actually I don't need to take it, the denominator. Let's leave the denominator alone. So I take this out, 1 plus x c minus 1. The denominator, let's write all of it here, 2c. Okay, so what do we have here? G prime x. And I have here 1 plus x. Okay, so I took out to the power c minus 1, so one of them is left here, minus c times g of x. Okay, so that's precisely what we proved. Okay, so we showed that this is 0. We just showed that this is 0. So this is equal to 0. Okay, so the rest is easy now. So hx is constant. Calculate h of 0. Okay, so this starts with 1. This starts with 1, so this is 1. So h of x is identically equal to 1 on x less than 1. Hence, 1 plus x to the power c is equal to g of x, which is the Taylor series of 1 plus x c. Okay, so now we proved one of the big theorems of power series, that binomial series can be opened up like this. Okay, to show how it is used, let's do some numerical examples. Okay, so example. Define f of x to be 1 plus x cube root. Okay, so when you write the terms of the Taylor series, this is going to be 1 plus 1 over 3x minus 1 over 9 x squared plus 5 over 81 x cubed minus, I'll use only this much, 243 x4 plus So this is typical of most binomial series. It is a term of positive terms for a while, and after that it alternates. If it's now it's we know that it is convergent. Okay, so we also check that the coefficients go to 0. So we can use the alternating series approximation. Okay, so we add up this part. Okay, so we use this part to approximate, and this part bounds the error. Bounds the error in absolute value. Okay, so we also know that this sum is larger than the actual value, because next time, in order to approximate, you have to subtract something. Okay, so let's. I put some numbers there. Okay, so let x be 0.7, and then I'll put 0.1. Okay. Then, okay, so where are my numbers here? 1.7. So 1.7 cube root is less than. Okay, so what did I do? Actually, here I did the following thing. I calculated this and wrote it here. I calculated this and wrote it here. So the error is in between. So this is what happens. 1.200, another 0.61729. And this is larger than 1.190181071. And this is actually, of course, you calculate from other methods to check if this is working. This is 1.1934 83192. Okay, so if you are not satisfied with this much precision, use a few more terms. And since the general term is going to 0 in this alternating fashion, it will be very precise. But you see, the real advantage of this is when you have x smaller, let x equal 0.1. Now the approximation is much better. Okay, so 1.1 cube root. Actually, I took, just to exaggerate this, I didn't took 0.1, I took 0.01 to show how fast these things converge. So this time you have 1, 0, 0, 3, 3, 8, 3, and 9. And here you have exactly the same thing. Etc. Okay, so it turns out that this much up to here is correct. Okay, so this is the advantage of using these. Let's do an exercise from the book. Okay, so in this example we had the power positive. So the example in the book is when you take power negative. So this says expand 1 over square root of something in terms of x. Use binomial series to expand 1 over square root 1 minus x squared. Okay, then we'll use this to find a Maclaurin series for arc sine x, because you see this is the derivative of arc sine x. If we integrate this, we'll get a formula for arc sine x, a Taylor series. Okay, so this one, let's see what this is. This is 1 minus x squared to the power minus 1 over 2. Okay, so binomial series, remember, 1 plus t to the power k is equal to 1 plus kt plus so why did I use k here? Okay, let me use c. I constantly use c here. So ct, c minus 1, 2 factorial, t square plus etc. Okay, so this is the formula. So put c equals minus 1 over 2 and t equals minus x squared. Okay, so that's, you do these things automatically, provided that the absolute value of x is less than 1. Okay, so here, so this is holds for t less than 1. So here this will hold when x less than 1. Okay, so then we have the formula 1 minus x squared minus 1 over 2 is 1 plus minus 1 over 2 minus x squared plus minus 1 over 2 minus 1 over 2 minus 1 divided by 2 factorial minus x squared square. Okay, so it goes like this. So you simplify this. So this is 1 plus 1 over 2 x squared plus 1 times 3 over 2 square, because you take these 2 here, and then here you have 2 factorial, and then here you have x to the 4. Let's write the next one. The next one is 1, 3, 5. Okay, so these are the numerators of these fractions, and in the denominator you have 2, 2, 2, so you have 3 of these, divided by 3 factorial, and x to the power 6. Okay, so now you guess the general term. The general term is you are multiplying odd integers, 1, 3, 5. So it goes up to 2n minus 1 divided by 2 to the n times n factorial x to n plus. Okay, so this is true. This equality is true when absolute value of x is less than 1. Okay, so integrating both sides, from 0 to x. Okay, so you integrate this from 0 to say t, and then you put t equals x. So we do it in one step. When you integrate this, you see this formula we remember as the derivative of sine x. Okay, the derivative of arc sine x. So we get arc sine x equal to, okay, so you are integrating these one by one. So what you obtain is x plus summation n equals 1 to infinity, 1, 3, 5 up to 2n minus 1 divided by, okay, we will take, this will be 2n plus 1 over 2n plus 1. Let's leave it over there. First, let us write this one. Then we have x 2n plus 1 over 2n plus 1. Okay, so this is the, and again we have x less than 1. Here we also geometrically know that we won't get a formula for when x is equal to 1, because at those endpoints the tangent to the curve is perpendicular, so algebra doesn't see it. Okay, so this is one way of using power series. So sometimes you use it to approximations. For approximation, sometimes you use it to get Taylor series of some other functions. Okay, let's do 2 more examples, and then we can take a break. Okay, now the other problem is expand 1 over 4th root of 1 plus x in powers of x. Okay, so we again write this as a binomial series, 1 plus x. This is equal to 1 plus x to the power minus 1 over 4. Okay, so the general formula is summation, well, this time I shifted to n equals 0 to infinity. This binomial coefficient with minus 1 over 4 there, x to the power n. Okay, so this is 1 plus minus 1 over 4, x plus minus 1 over 4, minus 1 over 4 minus 1 over 2 factorial x squared plus, let me write this one also because we want to see the pattern. Three factorial x cubed. Okay, you simplify this and you find the following thing. 1 minus 1 over 4x plus, the others are easy to write. Summation n equals 2 to infinity. You see, these are all negative things, so every time you multiply the previous term by a negative term, so the signs alternate. Okay, so that's why we have minus 1 n. Okay, so I don't have a parenthesis here. And check, you see that this is 1, 5, and then this is 9. Okay, so 1, 5, 9. And the general term, you check that you have to multiply something by 4 and then subtract something from it. It turns out that you are subtracting 3 divided by, and then the denominators here, you have n of them. Okay, and then you have n factorial, and this guy is x to the n. Okay, so this, you keep reminding yourself that this makes sense when x is in absolute value less than 1. Okay, so the next one is to estimate this, estimate 1.1, so x is 0.1. So you add up 3 terms. Okay, let me skip that one because numbers, you can put in numbers. So, okay, let's take a break here. This is all about binomial series. Next hour, we'll do a few more interesting things, and I'll stop by showing you that E is not a rational number. Okay, we can, with this information, we can prove that. Okay, so that will be the highlight of the course.